Have you ever looked up at the night sky and wondered what it's all made of? The ancient Greeks did. They gazed at the stars and contemplated the very essence of our universe. What is this stuff that makes up everything around us? Two great thinkers, Democritus and Aristotle, dared to ask this fundamental question. Democritus, a philosopher with a curious mind, imagined that everything was made up of tiny, indivisible particles. He called these particles atoms, meaning uncuttable in Greek. Atoms, he believed, were the building blocks of all matter, like tiny Lego bricks forming grand castles. Aristotle, on the other hand, had a different view. He proposed that matter was continuous, like a flowing river, and made up of four elements: earth, air, fire, and water. His ideas held sway for centuries, influencing alchemists and philosophers alike. The question of matter remained a mystery for ages. It was like trying to solve a jigsaw puzzle without all the pieces. However, the seeds of curiosity had been sown. The quest to understand the fundamental nature of reality had begun. Fast forward to the 19th century. A quiet English chemist named John Dalton was about to shake the foundations of chemistry. Dalton, a meticulous observer of nature, noticed patterns in the way elements combined to form compounds. He realized that these patterns could only be explained if matter was indeed made up of discrete, indivisible units: atoms. Dalton's atomic theory, published in 1808, was a watershed moment in science. He proposed that each element was composed of unique atoms, each with a specific weight. He also suggested that atoms combined in simple ratios to form compounds. This revolutionary idea provided a framework for understanding the building blocks of matter. Imagine trying to bake a cake without knowing the recipe. Dalton's atomic theory gave scientists the recipe for the universe. It provided a language to describe the elements and their interactions. It was a giant leap forward, pushing us closer to unraveling the mysteries of the atom. As scientists delved deeper into the atom, they encountered more puzzles. If atoms were the fundamental building blocks, what did they look like? Were they solid spheres, as Dalton had imagined, or something more complex? Enter Ernest Rutherford, a New Zealand-born physicist with a knack for groundbreaking experiments. In 1911, he conducted his now famous gold foil experiment. He bombarded a thin sheet of gold foil with alpha particles, expecting them to pass through with little deflection. To his astonishment, some of the alpha particles bounced back. It was as if they had hit something incredibly dense and positively charged at the center of the atom. This led Rutherford to propose a revolutionary model of the atom. Imagine throwing a tennis ball at a piece of paper and having it bounce back. That's essentially what happened in Rutherford's experiment. His discovery of the nucleus, a tiny, dense region at the heart of the atom, shattered the prevailing view of a solid, indivisible atom. Rutherford's model, while groundbreaking, had its limitations. It couldn't explain why atoms emitted light at specific wavelengths. The answer lay in the work of a young Danish physicist named Niels Bohr. Bohr, inspired by the emerging field of quantum mechanics, proposed that electrons, the negatively charged particles surrounding the nucleus, could only occupy specific energy levels or orbits. These orbits were quantized, meaning electrons could only exist at these discrete energy levels, not in between. Imagine a ladder where you can only stand on the rungs, not in between. That's similar to how electrons exist in specific energy levels around the nucleus. When an electron jumps from a higher to a lower energy level, it emits a photon of light at a specific wavelength, explaining the unique spectra observed for different elements. Section 5. The Quantum Revolution. A New Reality Unveiled. While Bohr's model was a significant step forward, it was becoming clear that the world of the atom was far stranger than anyone had imagined. Classical physics, which governed the motion of everyday objects, simply couldn't explain the bizarre behavior of particles at the atomic and subatomic levels. A new kind of physics was needed: quantum mechanics. Quantum mechanics, developed in the early 20th century, turned the scientific world upside down. It introduced the mind-boggling concept of wave-particle duality, suggesting that particles like electrons could behave as both waves and particles. It also brought forth the idea of quantum superposition, where particles could exist in multiple states simultaneously until observed. Imagine a coin spinning in the air. Until it lands, it's both heads and tails at the same time. That's the essence of quantum superposition, a concept that defies our everyday intuition but is fundamental to understanding the quantum realm. Section 6. Heisenberg's uncertainty, embracing the unknown. One of the most profound and unsettling principles of quantum mechanics is Heisenberg's uncertainty principle. Formulated by German physicist Werner Heisenberg, this principle states that we can never know both the position and momentum of a particle with perfect accuracy. The more precisely we measure one, the less we know about the other. This inherent uncertainty wasn't due to limitations in our instruments but a fundamental property of the quantum world. It implied that at the subatomic level, reality was inherently probabilistic, not deterministic. Imagine trying to pinpoint the exact location and speed of a buzzing fly in a dark room. The act of observing it with a flashlight inevitably affects its motion. Similarly, at the quantum level, the act of measurement inevitably influences the state of a particle. Section 7. Schrödinger's cat paradoxes of the quantum world. To illustrate the strangeness of quantum mechanics, Austrian physicist Erwin Schrödinger devised a thought experiment that has become a cornerstone of popular science: Schrödinger's cat. Imagine a cat inside a box with a radioactive atom, a Geiger counter, and a flask of poison. If the atom decays, the Geiger counter triggers a mechanism that releases the poison, killing the cat. If not, the cat survives. According to quantum mechanics, until we open the box, the cat exists in a superposition of states, both dead and alive. Schrödinger's cat, while a thought experiment, highlights the paradoxical nature of quantum superposition. It forces us to confront the limits of our classical intuition when trying to grasp the counterintuitive realities of the quantum world. Section 8. Beyond the Horizon, Mysteries Yet to Unfold. Today, quantum mechanics stands as one of the most successful scientific theories, explaining phenomena from the behavior of subatomic particles to the workings of lasers and transistors. Yet it remains deeply mysterious. We are still grappling with the implications of quantum entanglement, where two entangled particles, even separated by vast distances, remain connected in a way that defies classical explanation. The search for a unified theory that reconciles quantum mechanics with general relativity, Einstein's theory of gravity, continues to be one of the greatest challenges in modern physics. The journey into the heart of matter has been a long and winding road, from the philosophical musings of the ancient Greeks to the mind-bending discoveries of quantum mechanics. And the journey is far from over. As we continue to probe the universe's deepest secrets, we can expect even more astonishing revelations, challenging our understanding of reality and opening up new frontiers in science and technology. Section 9. The Atomic Symphony. A universe built on tiny wonders. The story of the atom is a testament to the power of human curiosity and our relentless pursuit of knowledge. It's a story that began with philosophical ponderings and has led to some of the most profound scientific discoveries of all time. From the smallest particles to the largest galaxies, the universe is an intricate tapestry, woven from the threads of atomic interactions. By understanding the atom, we gain a deeper appreciation for the fundamental laws that govern our universe and the interconnectedness of all things. So, the next time you look up at the night sky, remember the incredible journey we've taken to understand the building blocks of the cosmos. Remember the atoms, those tiny, enigmatic entities that hold the secrets to the universe's grand design. For within those infinitesimal particles lies the key to unlocking a universe of wonder and possibility.